Let's see here. Let's try that.
Okay. Yeah. Now it
Okay.
works.
Now, Dennis, can you hear me?
Yeah.
Okay. Sorry, I had something. Really, you weren't able to hear everything I was saying? Okay. So let's go over that. I was just introducing myself. Me, Franklin Hoot, John Chappell Natural Philosophy Society. Today is the 27th. Okay. So I was thinking that we would continue our discussions on the magnetic fields here. Let's see. Stefan was still saying that he couldn't hear me, but I think we hopefully fixed that problem, Stefan, because I had apparently something plugged into my microphone that wasn't a microphone. But you can hear me, right, Dennis? And there's James.
Yes.
Let's add James.
Hi, Franklin. I'm very excited today because I just got an email from Alex Dmitriev in St. Petersburg, Russia, who has been doing work on gravity and sort of debunking the equivalence principle of inertial and gravitational mass. And I have some slides prepared showing that of figures in his work showing that binary mechanics actually predicts all of his results that I can fathom thus far.
Okay.
So
well,
that,
like, you've got
as we get into today's session, excuse me, go ahead.
Well, it sounds like you got a topic. I was going to continue putzing around with magnetism, but if you have some latest breaking results with gravity.
Yeah, this is like
now, the
awesome stuff.
The equivalence principle says that basically everything falls as if it were accelerated. Now, you can't really tell basically the difference between those two situations, or that any object, no matter what its composition, it will fall at exactly the same rate. Right? But those the two ways I've heard the equivalence expressed.
Right, and like just about 5 minutes ago, I looked at my email on the other computer, and Dmitriev had answered a question I have concerning the horizontal and vertical rotors, because in an email to him, I predicted that the horizontal rotor would, in gyroscope, would weigh less. And it turns out that he confirmed that, yes, that's so, because in the English translations of his work, well, for whatever reason, I couldn't exactly find which of the two rotor types. So if you want, it's only a couple of, maybe half a dozen slides focusing mostly on his work. And the last several slides, I don't have a good explanation for. So maybe Dennis or Bob or some other people here would have a good explanation for those results. At any rate, should I show my screen?
Well,
get right
I'm
into it?
In doing that, although we do have some naysayers here. So, but just in the interest of letting you see the comments here, that I suppose, I don't mind that that you're bringing new things to the conference. So I'm excited to hear that. But I guess some people have getting a little bit tired of hearing about that. So just like I said, I don't mind.
Well, most of the bibble babble is about Dmitriev's work.
Yeah. Okay. So maybe we can make him happy by mostly.
I wouldn't call that bibble babble. This is a very ingenious man.
But sure, go ahead and share your screen and let's take a look at this research. I'm especially interested in anything that has to do with gravity.
Okay, here we go. Well, that's what he's doing.
Gravity is just one of these things that we don't understand, and as far as the equivalence principle goes, I'm not quite sure. Why should these things be equivalent? Acceleration be equivalent to gravity? One of the major dissident theories is that the surface of the Earth is actually accelerating upwards at 9.8 meters per second. And that's another way you can see why they would have to be equivalent, because it is an actual acceleration. And the only reason why my butt is being pressed against the seat is because the surface of the Earth is accelerating upwards at 9.8 meters per second. And that's like a literal interpretation of the equivalence principle that is not equivalent. It's like it would in fact be exactly the same thing. And that's why when you drop anything, they would actually fall at the same rate, because when you drop something, all that's happening is that this thing stops accelerating, and then the Earth would come and meet any particle at the same time. So, but if you show something that's not necessarily true, then that would be interesting. It's also like a problem with my electrostatic gravity proposition, because people say, well, if gravity is electrostatic, then you think it would have to interact with different materials in a different way. So if you have a completely electrical charged metal ball, that should accelerate at a different rate than, say, the highly charged styrofoam ball, right? So, but that's not the case. It's a styrofoam ball, metal ball in vacuum fall exactly the same rate, right? So I have to argue against that there is no effect based upon the material. But let's see, we've got your screen share now.
Okay. Thank you for the introduction, Franklin. Okay, we start with a little bit of bibble babble, and before we get to the slides of that are actually figures from Dmitriev papers. This is the slide I showed before in the session on quantum gravity mechanisms. And it's just simply talking about the law of motion, that objects tend to move in the direction of higher bit density. Here in the X dimension, if we have a higher quanta density here than here to the left, all else being equal, and yes, there could be many other forces acting on the object. So we're just going to say all else being equal, the object will move to the right toward the higher bit density. That's the motion law. That's a repeat from a previous slide. Now I break it down a little bit in more detail here, because a lot of people didn't quite understand that before we get to Dmitriev's slides. On the left are 9 locations in the hexagons, and the black circles are 1-state bits I call quanta, and these are 0-state locations are bit loci in these 9 locations shown in the XY plane at time equals 0. A particle is defined as having a certain minimum number of quanta, let's say 3, shown in yellow here at time equals 0. Notice that the quanta density gradient is pointing downward in the Y dimension in this illustration. The upper row has only 1 quanta per location. There's a mixture of 2 or 3 in the middle row and 2 here in the bottom row. Okay, so in other words, the density is higher in the bottom row than in the upper row where the density is lower. Now at time equals 1, if 1 quanta from here moves to a location in the lower row, now the particle has moved, because our criteria for a particle is to have 3 quanta in a location. And so here is our quanta density gradient. Now the last slide I have concerning what I'm presenting to you about a quanta density gradient, before we get to Dmitriev's slides, is here we can talk about what's going on with 2 objects which are not two objects which are not in contact. In that case, in the lunar laser ranging study, we showed that higher surface temperature appeared to increase gravitational force between Earth and Moon. No, but what about in Dmitriev's work, which some of it has to do with an object that's stationary on a scale? The virtual space between the scale and the object resting on the scale is represented with electrostatic repulsion between the object X and the scale. Now, here is our density gradient of quanta, which we can assume that the gravitational vector G pointing down towards the scale and the Earth, weighing object X, represents a quanta density gradient, which I just showed you some of the details of that, pointing toward greater density. Now, secondly, assume particles in X, everything from nucleons, electrons to atoms and molecules, occupy only a fraction of the volume of object X. That is, most of the volume of X consists of quanta density gradient G prime, perhaps of somewhat decreased magnitude due to the disruption by particle motion. In other words, within the object, we're also going to have a quanta density gradient. Now, first slide with, we showed this before in my quantum gravity mechanisms, where Dmitriev, in this paper cited here, showed the change in apparent mass, the weight in milligrams, over time, minutes, of a brass rod with ultrasonic heating starting here and ending about here. And we see that the weight of the object as it is heated decreases, okay? And this is the actual slide that I included previously of the same data from Dmitriev. And at that time, I said that infrared radiation from the heated object would deliver momentum away from the heated object toward other objects, causing a repulsive effect. And this may in part explain the decrease in mass that Dmitriev observed. Now here is another study by Dmitriev, where he has time development dependence of a container with a container mass by heating a PZT pile of piezoceramic from 24 to 25 degrees. Those are the vertical dotted lines. So here he plots two variables on the y-axis here. Here he's showing the temperature going up and the apparent mass of the entire container containing the piezoceramic material, which was heated, its temperature going down during the period of heating. And if the temperature is maintained at this level, so the weight loss or the decrease in I guess this is MCG. What? Let's see. That's not milligrams. That would be, I think, micrograms. Oh, okay. MCG. That decrease in micrograms continues on as long as the temperature is raised. Now, what I'm saying in both of these studies of Dmitriev that we have just seen, the heating is going to increase, and Dmitriev himself says this in his papers. The heating would increase the thermal motion of the particles in the heated object, where the weight is seen to be reduced. So what I'm saying is that what I showed you in my Bibble Babble, and thank you for that term, I'm going to continue to use that. I love it. In my Bibble Babble section at the beginning of this presentation, this brief presentation, that this increased thermal motion would decrease the gradient within the object of quanta, and therefore it would weigh less because of the motion law. There'd be less of a tendency for particles within the object to move to the higher gradient area, which would be downward toward the scale. If there's less such movement, the object will weigh less. Now, is Dmitriev finished? No. This is ingenious here. Change of weight of optical fiber. Dig it, man. Under the impact of laser radiation. Dmitriev and co-authors in St. Petersburg at the Technical University present results of high precision weighing of sealed containers holding coils of fiber optic bundles. Now, who would have thought? While stimulating these fibers by radiation of helium, neon, and semiconductor lasers, okay, weight decrease of fiber was observed during dissemination of the laser light. The weight reduction remains for a few seconds after the laser is turned off. The article offers explanation. Here's his graph. You see the weight reduction remains a little bit after the turning off of the laser light being sent into the optical fibers in the object he's weighing. Now, again, what would my bibble babble predict here? My bibble babble would predict that the laser light would tend to destroy and disrupt the quanta density gradient within the fiber optic fibers. Therefore, and reduce that gradient, and therefore we would see the observed weight reduction here that Dmitriev observed.
So can I interrupt you right here, James?
Yeah, please interrupt, of course.
Because I'm just not getting that that the heating would cause this. You're talking about a gradient, and as far as I can see, say within a optical fiber, there's no gradient. There's just some temperature. So I don't see the connection between how increasing the temperature would lead to a prediction where that would change the quanta density any.
Okay.
I mean, the quanta density corresponds to, as I say, the number of detectable particles present. Then when you heat something, that does nothing to the quantity, nothing at all. And if you have to take those particles and you move them around rapidly with thermal energy, that still doesn't do anything to the density. So that's why I don't understand. I don't see it following.
Oh, okay. Well, there are two things here. Dmitriev's results, which stand on their own merit and can be interpreted as you might wish. The second thing is my predictions, which we might from the Bibble Babble, and to address what Franklin just said, we're going to assume that particles in the object X up here, everything from nucleons to electrons to atoms and molecules, occupy only a fraction of the volume of X. In other words, this gets back to my vacuum composition paper and video on of the same title. That most of what is thought to be empty space in solid objects is in fact teeming with quanta. And now I'm saying that empty space can have the same density gradient as might be observed in the gravitational field strength, as it were, outside the object. In other words, we have a quanta density gradient both outside and within the boundaries that we normally would look at in a solid object, like for example, Franklin's billiard balls.
So, because I know that's true for a fact, because you could just look at the atmospheric pressure, and that's definitely a quanta density. Definitely, the density of the air at the floor is much higher than the density of the air, even at the ceiling of my room. It doesn't take very much to create that kind of gradient. Well, so that's the kind of gradient you're talking about, just like the same one that's
if I may, yes, I mean, the actual objects are particles in the air is what is thought to cause atmospheric pressure. So in the classical version of pressure, they're really, in statistical mechanics, I believe they're talking about the actual force of the particles on the side of the container. And these would be formed particles like atoms or molecules of gas. Yes. Now, but what I'm saying here is that in addition to those particles and the quanta in them, there is also, according to my vacuum composition paper, most of the quanta are in fact in what we would call the perfect vacuum, the so-called empty space, both within an atom and around atoms. That is, down here, the last sentence, most of the volume of X consists of a quanta density gradient G, perhaps of somewhat decreased magnitude due to disruption by particle motion. Now, the first slides, and I want to skip back to Dmitriev's work because I want to highlight his work here. Yes, I think my work predicts his results, and you can agree or disagree with that. But also, we can just look at his work as a standalone piece of scientific effort and evaluate that also, okay?
Yeah, but that's
So
not.
should I now?
Just want to clarify, that's the problem that I have, is that I don't see how your theory predicts that increase in temperature results in decrease in gravity. That's what.
Okay, good question. I think you have pointed out a real gap in my presentation. If we start from this last sentence, most of the volume, here's where the gap I think is that Franklin has just pointed out. Thank you, Franklin. Most of the volume of X consists of a quanta density gradient. So now how would increase in temperature decrease weight? Well, if the particles, as Dmitriev says, and the classical textbooks say the same thing, are moving with greater velocity within object X with increased temperature, that is going to disrupt the quanta distribution with in the perfect vacuum section or area or space within the object and reduce the gradient. That's what I'm saying.
No, it wouldn't.
To explain.
That's why I'm disagreeing with you. I would say that if there's a gradient in, say, a pot of soup, you're saying that if I stir the soup, that's going to significantly disrupt the gradient. But I don't think it would, or maybe it would. I don't. Maybe that's a better analogy. If I
love your analogy. I love your analogy.
If I had a pot of soup and I had all the heavy meat at the bottom and the light noodles at the top or something, because that's a gradient, right? And maybe if I boiled the soup, then we'd see that the meat is now more uniform inside the pot, I suppose. Maybe that's what you're talking about.
I love your analogy, but let me go with a better one that I like better anyway. How about a gallon of paint, of oil paint, that has been sitting for months and months and months? You know, when you open it, you have to stir it because there's a density gradient of the pigment particles that have settled toward the bottom. And it precisely as Franklin just pointed out with the food example, that stirring is going to reduce the gradient of those pigment particles so that the paint at the top has about the same density as at the bottom, and then you're ready to use the paint to paint the wall. Okay, so I love that example. So in other words, I'm saying that my bibble babble theory predicts Dmitriev results because increased temperature would disrupt or reduce to some extent the gradient. Maybe not entirely because he has a limited range of temperature increase. But he does have a measurable amount of decrease in weight.
Well, we're getting closer here. So you're saying there's a change in gradient. Okay, I can accept that. But still, I don't know how that would have any effect upon the gravitational force. I mean, it's like, so what?
Because the motion law. The motion law is that objects tend to move in the direction of higher density. If there's no gradient, then the particles within object X that you are weighing will have less of a tendency to move downward, applying pressure, if you will, to the scale, and which registers weight from that pressure measurement.
That still doesn't follow. I mean, even if there is an internal gradient in object X, then, I mean, the thing that's actually causing the motion here is still the quanta density difference higher towards the center of the Earth, and that quanta that's the main gradient that's causing the weight. Whether that particle is in the bottom of your object or it's on the top of the object, whether it's moving around in the object, shouldn't really have any a net effect upon the entire object itself, right? Whether, if I put like one individual object inside that little box there, your object X, and I can say, okay, it's stationary. It's being pulled by the density gradient. Cool. Now I take that same object and I just like bounce it around like a bouncy ball. And at any point, that same object would still be under the same influence of the density gradient. And I would say that it just shouldn't matter whether that object is stationary or whether it's bouncing around. So I don't see how your theory would predict that the box with the one particle bouncing around should weigh less. I mean, that's just simplifying. That's how we do science. We just simplify it down to the simplest thing. So let's just think about one particle in your object.
The simplest thing is that what my work says, or claims, is that there is a quantum density gradient, like in our bodies, in any object that we weigh on a scale, and that certain activities, such as the stirring you mentioned for the food and me with the paint can, can decrease the gradient within the object enough that we get a measurable decrease in weight on the scale, which Dmitriev's data shows. So that if you don't like my explanation, that's okay. But the question is,
I don't understand
how do you explain Dmitriev's data?
Because there's lots of other things like I definitely know though. Charles Lucas, Dr. Bill Lucas is on watching us on live stream. I'm sure he's screaming because I've heard his explanation many times, because he also points out this exact same data, and he believes that gravity is caused by the vibrations between the quadrupoles or whatever. That it so that the actual gravity is due to how just directly related to how these vibrations between these particles happen. So his explanation is that if you heat them, then obviously these bonds become larger, and that's what causes the decrease, right? Hopefully, now if I got that wrong, then feel free to come on the live room here. We've got plenty of space, Bill, so you can, if you want to give your alternate explanation. I mean, I as well have an alternate explanation. And, I explain it as, since to me, gravity is just the electrostatic force. And in order for the electrostatic force to work, your dipoles all have to align from whatever random orientation they were. They all have to align so that they're pointing towards the Earth, right? So that you have one pole directly pointing at the Earth, which is just basically a large positively charged ball. So you'd see all of the dipole molecules and everything with a negative end pointing towards the positive Earth. So what happens is that if you heat the dipoles, then that would cause them to not point towards the attractive positive thing. And when you start doing that, then that would directly decrease the attractive force to those dipoles. So that's another way to explain why is it when you increase the heat, it kind of appears to decrease the weight. So there's a number of.
Okay, well, Dmitriev has some more surprises for us, and what Bill Lucas' theory that you cite is not necessarily mutually exclusive to the predictions I'm making based upon a quantum density gradient. They both could account for part of the results. But I didn't want to monopolize with too much of my babble per your comment that you showed at the beginning of this session. So can I get back to what Dmitriev is doing?
Yes. What other results?
Okay. I'll go forward here. This I've already covered. This is the piezo ceramic. and then we went and we covered this, that the apparently putting a coherent laser wave into these optical fibers can, according to my work, I don't know how Bill or other theories would account for this, but it would predict a disruption of the quantum gradient within the optical fibers again, in that which is most of the volume now of those fibers is not the particles themselves, but the so-called empty space between the particles, and we see the weight reduction. Now let's go to a new slide. Here's the one where I couldn't quite interpret what is going on here in this graph. And again, he's showing the frequency of rotation leads to looks like with this standard, with this error bar, a possibly significant difference, again, in, I guess, mg, that's milligrams, in mass. And so, yeah, I wasn't clear. So I wrote an email last night to Alex Dmitriev, and he just replied minutes before this presentation that I had predicted that the horizontal rotor would weigh less. And that's what he said, compared to the vertical rotor in a gyroscope. Okay. And maybe this graph doesn't exactly, it shows something a little bit different or whatever, because he's showing that also the frequency of rotation, what he's calling the mass difference here is greater, with a greater frequency of rotation. All of this, well, first, the frequency of rotation being a factor in reducing the mass, and particularly of the horizontal rotor compared to the vertical. And by the way, he put in 2 rotors in one container, rotating in opposite directions. So the total moment of angular momentum of the container would be about 0, because the 2 rotors were rotating in the container that's being weighed, were rotating in opposite directions. This is how clever an experimentalist and thinker Dmitriev is. Now, he just replied. I asked him, I said, look, I can't figure out from your paper which of the 2 rotors, horizontal or vertical, weighed more or less. And I had said in a previous email that I would predict that it was the horizontal one. And why would I? And he confirmed that. Yes, the horizontal orientation weighed less than the vertical rotation. And by the way, it's not 2 different things he's weighing. He just changes the orientation by 90 degrees of the container with these rotors in the container. Now, why would I predict the horizontal rotor would weigh less? Because if the math is done with the geometry, and he does show a picture, which I haven't included here, of the actual container and the size of the rotors relative to the size of the container and so forth. And there's 2 of these rotors, as I said, rotating in opposite directions. With the horizontal rotor, I think would be more disruptive of the quanta gradient, because its span of angular momentum would have a greater vertical span within the container than the vertical rotor case. And so therefore,
by a horizontal,
excuse me,
what? Because for me, it's not clear what that exactly means. So if this is
what means
thing is my rotor, then is this the horizontal orientation, and is this the vertical orientation? What does he mean exactly?
Well, again, that's why I wrote him an email, because it looks like this figure here is showing the dependence on the frequency of rotation. And that's why I emailed him.
I need to get this clarified, because it's like, what's horizontal? Is it the axis that's horizontal, or is it the mass?
Yes, the axis of the rotor is horizontal. Yes, correct.
So what is it? Is it the axes?
The axis of the rotor. In other words, it's horizontal with the scale and the Earth. as opposed to if you turn it 90 degrees, then the axis of the rotor, or the central bar in the rotor, or gyroscope, if you will, would be pointing up. But if it's horizontal, it's parallel with the surface of the Earth and the surface of the scale weighing it.
If we're talking about the axes, then this would be the horizontal orientation with the axes running through here. Is that an agreement? That this
what is this? This I think has this figure.
That's a yes or no question.
I invited Dimitri.
No, please don't give me long explanations. Is this, to your understanding, the horizontal orientation? So the gyroscope is rotating this way. This is what he means by horizontal.
In the figure? In the figure I'm displaying right now?
Yes, I'm trying to figure out what does he mean by horizontal.
That's what I don't know. That's what I could not figure out.
Is this the horizontal orientation? Because this could be the horizontal orient if you're talking about the axis. So the axis is horizontal.
Well, I don't know which it is.
But the most
I do not know which it is, but I do gather, and he states this in his article, that the effect of the mass difference is greater at a higher frequency. So because I did not know the question that Franklin just asked, I wrote to him an email and said, which one, horizontal or vertical, weighed less? And he just replied and said, the horizontal weighed less.
And that's great.
That's not in this figure.
Orientation, that is. He needs to provide a figure saying, this is the horizontal orientation and this is the vertical, because we don't know whether he's talking about.
He does provide a figure. And as I explained, in that figure, the horizontal situation is where the rotor or the axis of rotation is horizontal to Earth. If you point the rotor up,
right? So that's all I was asking. So that's why I wanted to know. So I don't know why you said you didn't know, because that's what we need to know. So if this is I
didn't know until he told me in an email about 15 minutes ago.
Okay, so this is what he means. If this is the horizontal orientation, right, of the spinning object, like that. It's not this.
What is this? What is this that you're saying? This
is.
Are you referring to
this is the only thing I have to represent a spinning gyroscope. So I have
Franklin,
this, and I can spin this way.
Franklin, we can't see you. Franklin, we can't see you. The camera is not on you.
Oh, that's right. Sorry. Excuse me. Yes, sorry for pointing out. Okay. All right. So the only thing I have to represent a gyroscope is my roll of tape. Okay. So the only question is, what does he mean by horizontal? So is this what he means horizontal, meaning that the axis is horizontal, right? Is that what he means? And then this
I can't see you because I'm displaying my screen, but horizontal would mean that you would put the roll of tape on the side, on its edge, so that the diameter of the roll of tape would be perpendicular to the table.
So
got it?
Go with that. So
that's horizontal.
Horizontal, so that the tape is perpendicular to the table, right? Okay, got it.
The diameter of the tape, the tape is the tape. I'm talking specifically the diameter of the tape is perpendicular to the table.
Okay, right. If I put a diameter mark on my tape, then that would be perpendicular to the table. So we are talking about the axes being horizontal, right? Because I think
that's what I've been saying over and over.
The axis is pretty clear, right? Okay, so in that case, you have the particles moving up and down within the gravitational gradient, right? As it turns, it'll be on the bottom part, and as it turns, it becomes the top part, and it'll go to the bottom part, as opposed to vertical, as he's saying, where the particle just keeps on riding at the same height as it goes around. And in that case, we don't see any gravitational attraction difference. Okay, got it. All right. Yeah, that's a big difference.
So in other words, you have to explain all of Dimitriev's data. And I'm not excluding Bill Lucas or anybody else's theory. that could also be a factor in this. And it repeatedly in Dmitriev's paper, he's very humble because he's saying over and over there's many factors that could explain these results, and he suggests some of those factors like the thermal motion of the particles, and I agree with that explanation. And I'm saying that that's like mixing the paint can to reduce the gradient of the pigment for a paint can that has been sitting there for a long time, and the pigment has settled more toward the bottom. Now, if I may, I'll go on to his next.
Stirred or
There's several other slides here, and that's it.
Upon the overall density. So,
that what?
See, my point is whether you have a can of paint which is settled or a can of paint which has just been stirred, the contents of both of those cans of paints are identical still, and that is what causes the gravity. I mean, whether the can of paint is uniform or whether it's not uniform has no apparent effect upon how it should be attracted by any gradient which exists on the outside. That just doesn't follow. At least in my opinion, I don't see how it follows. Maybe it followed, but whether it's stirred or not, it's still.
Well, it's an analogy. It's an analogy, Franklin.
It is, but it doesn't follow.
Analogy
it doesn't follow.
To portray the idea that the gravitational gradient, which is I'm saying is in fact the quanta density gradient within a weighed object, can be disrupted by mixing and by all of these effects, by light in optical fibers, according to Dmitriev's work, by heating it. And now we're talking about some other things in terms of vertical and horizontal quasi-electric impacts of where solid metal balls are accelerated toward a heavy metal plate, and he's measuring the coefficients of restitution and showing that with increased velocity on the horizontal scale here, before impact, that the vertical and horizontal impact situations gives him a different coefficients over here. And he is presenting this as yet again additional evidence of a dissociation of inertial and gravitational mass, okay? How this relates to the mixing idea that I have presented at the beginning, I'm not sure, but that's one reason to present this here. And I wish Dmitriev were here to speak for himself. But at any rate, this is, I guess, almost the end, if not the end. Measured values of acceleration. So now we're going to objects which are not placed at rest on a scale to weigh them. Measured values of acceleration of free-falling gyroscope with horizontal rotor bars. The first bars here, the first four, are the grams, I guess, or his measure of acceleration when the rotor is stationary. In other words, it's off, it's not spinning. And then these center bars show an increase in this free fall acceleration when the rotor is spinning. And then when the rotor comes to rest after a period of time, we return to our baseline, our control level here. So here he's showing that the actual acceleration of an object is increased, okay, with the gyroscope actually rotating. Now, is there another slide? Let's see. No, that's the end. Oh, okay. I'm going to take the slideshow off and get back to being a normal human being here. There I am, a normal human being. Ha ha.
Okay, so let's discuss the results. So we know that gravity is affected by heating. You know that gravity is affected by apparently even light through a optical fiber. We know that gravity is affected by spinning in a gyroscope, and we know that the acceleration is affected also by a gyroscope.
And also the impact, whether the impact is vertical or horizontal. And this may relate to my hypothesis concerning the disruption of the quantum density gradient, which is in fact the gravitational potential gradient. Book.
Okay, I think I'm back.
I haven't. Definitely shows a difference between horizontal and vertical. And by the way, Dennis Allen modeling of this and may have some insight about this, because I'm presenting this because I that particular impact experiment, both horizontal and vertical, as well as the very last slide I showed in terms of the acceleration with the rotor spinning being greater in a free-falling gyroscope than with the rotor not spinning.
Now, see, I don't understand your theory. Why would there be a difference between the horizontal versus vertical spinning? Because in both cases, the particles are translating in space just the same. And I would predict
no,
that
it's not. Well, obviously, I'm saying it's not just the same.
Stirring just as much, whether it's horizontal or vertical. So why would you predict a higher gravity only in the so-called horizontal case?
Well, actually, it would be less weight of the object in the horizontal case, where the rotor is horizontal, much like the axis of a bicycle wheel. That when the bicycle is erect and you're riding it, let's say, the bicycle wheel, the axis is horizontal to the earth, because the wheel is standing on its edge, as it were. Well, with the wheel standing on its edge, with the horizontal axis, what I'm saying, and Dmitriev, and I'm sorry I didn't show the illustration because he has the illustration of the actual rotor in the container that he's weighing, pair of rotors actually, rotating in opposite directions, as I said, to make the total container angular momentum 0, according to what he writes. I can do, one can do measurements that perhaps with the horizontal rotor, the vertical mixing and disruption of the quantum density gradient would be greater than with the vertical rotor, much as Franklin just said. Why would I get out the map? How wide is it?
It shouldn't be any difference at all.
Well, you might say, well, let's do an experiment. I'm giving you the working hypothesis.
Going around, say, 1 mile per hour. Now, it shouldn't matter which orientation it is. It's still disturbing the space exactly the same at any.
Let's go back to our paint can. If I had a ball, just say at the bottom or at some level above the bottom, horizontal with Earth, in the paint can, and it was spinning around, it would tend to mix particles or quanta of the same density in that vertical volume that we could look at with the ball spinning around, perhaps magnetically, like they have in chem labs, a little magnetic thing under the container to make the ball spin. But on the other hand, if I'm mixing the paint and the mixing rod that I'm using, if I lift it up and down, I know that I'm going to mix that paint faster than if I just simply stir it circularly and at the same depth over and over again. I know that the paint is going to mix and get ready to paint my wall faster if I lift up the heavy, dense stuff at the bottom and mix it with the stuff at the top and mash it all around, etc. Like in a coffee grinder, I don't know why I just bring this up. I have a coffee grinder setting right next to me. the blades are set up in such a way that material at the bottom will tend to come to the top, so that beans which have not been ground up yet by hitting the spinning blade will be mixed up and around in there. And obviously, the beans that are not yet ground up yet might sink to the bottom otherwise, but the blade is designed to sort of lift the so-called heavier material at the bottom, so the beans get completely ground up for your coffee. So,
Frank, to get why that would work. Now, I understand that your theory is that if you have an object,
try mixing some paint, and you'll see what I'm talking about.
If you have an object and it will move towards the region of higher density according to your theory, right? I'm just trying to understand your theory. So I have an object, and if the higher density was like over here, then the object would move towards that higher density. So you have to
Exactly.
justify.
That's
You have to
motion law.
justify that a region of space which is in motion in your box is somehow exposed to a higher, or actually a lower region, because the main thing here is your space and the gradient density in space. I would imagine what's in the box.
The region of space is not in motion in my work.
Well, just a minute. What's in your box is not actually has an effect upon the overall weight, right? It's the gradient. So you have to show that the gradient somehow decreases when this box is in motion. And I don't see that.
Well, the box is not in motion. It's on a scale.
Yeah.
The space is not being mixed either. In binary mechanics, space is a stationary cubic lattice of spot cubes. So we're not mixing space.
I'm saying that
we're mixing quantum.
Let me try and clarify my point here. So please try not to interrupt me. I will stop and then we can ask questions, okay? But don't interrupt me while I'm trying to give you my explanation of why I don't agree with this, right? I think what you're saying is wrong, okay? Which is fine. This is what scientific debate is about. I'm saying you're wrong. The reason why I'm saying you're wrong, I will give you this specific example. So let's simplify the system down to a box with one particle in it, okay? Now, we know that according to your theory, that particle will be attracted to the higher density difference, which will be towards the Earth. Okay, we got that. Okay, now the contention is that there's going to be a difference between that inside that box, a stationary particle versus one which is bouncing around in the box. Okay, there's the one that's bouncing around the box has got more thermal energy. And you're saying, but in this case, the density hasn't changed around the box. Nothing has changed about the gradient difference around the box. The only thing that's happening is that this ball is bouncing up and down, and any given location it is in the box, it will have some attraction to the ground, and that's what we weigh in the box. Now, whether it is moving up and around or whether it's stationary, it's going to pretty much weigh the same, right? So I would say that your theory does not predict that the bouncing box with the ball with the bouncy ball in it is going to weigh any different than the one that just has a stationary ball in it. That's my assertion. So I could be wrong.
Well,
so
it's contrary to Dimitriev's data. He shows, and I'm convinced. You can look at his data and say you're not convinced, but I'm convinced that he has shown quite well
that
increased temperature reduces weight. And so what you're saying is that increased temperature with the movement of the particle would not increase weight. Well, would not decrease weight. You say, well, that's contrary to Dimitriev's data.
Hold on. So you didn't address at all the little thought experiment I just made, which you have a box with one particle in it. So you have to show that the box with the particle in it that's moving around is going to have less attraction than the one where it's stationary.
Well, that one particle moving around would tend to disrupt the gradient, just like when you're mixing your paint. Okay? It could be a million particles, a trillion, or just one. It's all a matter quantitatively of how much disruption of the gradient you're going to have. And the data is provided by Dmitriev. And I hope maybe some other people have done experiments along the same line. But he not only did temperature, he's done the laser within the optical fibers, which would tend to disrupt the it's plausible to say that also would disrupt the quanta density gradient in those optical fibers and showing the weight reduction. Furthermore, he's shown that the horizontal rotor. So what you're saying, basically, Franklin, and I welcome the questions because that's why I presented this to get some clarification from other people as to what they thought about it. But the horizontal rotor is going to mix the paint more than the vertical rotor.
Now, this is the other problem.
We find that the horizontal rotor weighs less. Hey,
this is a big problem for your theory, James, because you're saying it should be more, but it's not more. It's in
I'm saying it should be less. I predicted that the horizontal rotor would weigh less.
Your theory must predict that there must be some weight loss between spinning and non-spinning at any orientation. That's what your theory must predict. But we find that in vertical, there is no weight loss at all. Your theory would have to predict.
I didn't say that. I never said that.
That
as far as I know, that's not a result. As far as I know, that's not a result.
Well, once again, I would assert that your theory, if it has to do with stirring the gradient is equally stirred by horizontal or vertical. It's going to be some. It can't be zero.
Franklin, the data from Dmitriev is if I remember that graph correctly, a weight difference. It's not the weight of a horizontal rotation. It's the difference between the vertical and the horizontal. So in both cases, vertical and horizontal, there is weight loss. But what's plotted is
I think so. I'm thinking
the plot shows the difference between the weight loss of vertical and the weight loss of horizontal. That's why it says difference.
Well, I guess that would be another question for Dmitriev. The way I was interpreting it was that there were two lines on that chart. One was at 0, flat, and another one had a curve on it. Now, it could be. Maybe that's correct.
Well, as I said, he has answered that question. You're saying it's another question for Dmitriev. He's answered that question about 15 minutes before this session started in an email saying that the horizontal rotor weighed less than the vertical rotor.
Yes.
So you could say that he's lying or he's fabricating data. You could criticize his methodologies or the statistics is not significant enough, but that is what he said. Okay, and what he said is what my theory would predict.
So I want to make clear, your theory would predict clearly that both rotating rotors should weigh less.
Yes, because there would be some mixing in each case, wouldn't there be? And
that's what I'm pointing out. Is that what his data showed? From what I understand is that there's a very big difference that whether it was that's very important. You got to take both rotors, non-rotating and rotating, in both orientations, and so there should be a chart with like these 4 things on it, and that's what we need to go off of to be clear, because that is also an important.
I asked him precisely that question, and he answered it. You can accept his answer or not. Okay.
So
what you're saying is you don't like the graph that he posted in his article. that
So
his
was there
artwork
any
or
weight
his
difference
graphing
in
of his
any
data,
vertical?
he could have made another graph, but I asked him point blank which weighed less, because it was not clear to me from the
Well, this
graph
is
that
the
he
question.
presented which weighed less.
If you know
And
the answer, you need
he
to tell me.
replied. So you can say he's lying or he fabricating the data. You cannot accept that, whichever you want. But I think we're spinning our wheels here. Let's
No, we're
just
not.
accept
I
the
mean,
data.
if this is the so-called vertical orientation, if you have one of these that's spinning versus one that is not, ask him, is there a difference in this case? Right? Now, you said you got the answer.
I did.
The answer.
And he said that the rotors have to be spinning for there to be a weight difference.
Is there a
Absolutely,
difference
yeah.
between a spinning
That's the whole
rotor
point of his paper.
in this orientation versus one that is not spinning? In this orientation.
Right. The weight loss is only when the rotors are spinning. Correct.
No,
he showed that
that's not saying whether it's this way or whether it's this way. Specifically, if the rotor is spinning this way, does it experience weight loss at all?
Well, you can have a what would be like a vertical rotor by just simply having your stirrer in the paint can reach the bottom, stay touching the bottom, and move it around circularly, and some mixing will take place.
Let me stop you. I'm not talking. I'm trying to figure out what the experimental result was. Not anything about your theory. It's a very simple question. Is that when the rotor is in the vertical orientation, when you spin it up, does it lose weight?
My understanding is yes, but if it's in the rotors in the horizontal orientation, it loses more weight, according to the statement I received in written words before this session started from Dmitriev in an email. That's what he said. Because the graph, as you rightly point out, the graph is confusing.
That's not a clear statement of what's happening there. Because for me, I guess it's more important because, like I said, my theory would be that the particles are always trying to align towards the Earth's center, always. Now, anything that you can do to cause them to be not aligned would decrease the effective weight. And certainly, if you had a particle and you start spinning it around and try and change its orientation constantly, that would be a very, very good way of taking. So if it was pointing down this way, as soon as it went up to the top of it, it'd be pointing in the wrong direction. So it would have to constantly turn in order to maintain its pointing towards the Earth. And that's why, for me, that definitely explains why is it that when you increase the RPMs, the more you do that, the more it decrease the abilities of that particle to point towards the ground. It was as if you had a bunch of compasses and you stuck it in a wheel, and you had a big magnet at the bottom that, if there's still, then all those magnets would be pointing right at the magnet. But as soon as you start spinning that thing around, all the little compasses still going to try and point their end towards the magnet, but they will not be able to. Some of them will not be able to point fast enough. So that's and I can say that is more convincing than, I still have a hard time understanding your gradient thing. So you're changing, I understand a little better because you're changing the gradient of the gradient inside the box, I guess. So that I guess I can kind of see that it undisturbed, the gradient at the bottom of the box would be greater than the gradient at the top of the box still. So if I were to mix up the contents of the box, then we would see that we no longer have that higher gradient in the bottom of the box kind of thing. So I could kind of maybe see that. So I think I'm seeing that a little bit clearer.
Particles of pigment in a paint can, and you seem to accept the fact that stirring the paint can with either vertical or horizontal motion of your stirrer will do some degree of mixing. And in both cases, the weight loss will be observed. But if you do more vertical mixing, in other words, with a horizontal rotor in this case, the weight loss will be greater. And that's what Dmitriev's result appears to show. And as far as I know, he's the only one who has confirmed this. And so what I understand Franklin to be saying is that he agrees that, yes, you can stir things up one way or the other, and there should be an effect of that stirring. And well, wonderful. I mean, frankly, I'm sitting here asking, what is exactly the disagreement here? I don't even know what it is.
Well, the disagreement, I think, is the mechanism by which the stirring decreases the force. And getting back to Bill's theory, however, of vibrating dipoles, I mean, I think the rotor experiments are a much bigger problem for his theory, because once again, the rotation doesn't really change the nature. I mean, it's not a heating case. So Bill's theory works in the case of heating. So he can explain like the laser result. No, the laser result could just be due to the heating of the photons through the cable, and that's why the effect lasts for a little bit, because it just cools off, you know. But the rotor case is not a case of heating. The temperature of the rotor is not changed significantly in this case, but yet we have an apparent decrease in weight. So this is something that would be hard for Bill's theory to explain. Once again, Bill, if you have an explanation for why, you know, no change in temperature, just, you know, change in orientation seems to have this kind of change in weight difference. So that's a big problem for, I think, the vibrating dipole thing. But you do mention that Polja is basically the only person who kind of has this data. If you ask mainstream, they would probably just kind of disagree with it on that basis, that, you know, he's the only guy who did this, and so maybe he just did it wrong. I mean, some things.
Well, he's not the only one. He cites work going back many decades, back to the 1920s, or perhaps even I have the date wrong, but a long time ago, before general relativity came into place, where people were exploring the effects of temperature on weight. And the temperature effects is what he's calling I guess elastic forces, of the electromagnetic nature interacting with the gravitational field. And so he's trying to show a lack of equivalence between inertial and gravitational mass, and he brings all of this theoretical stuff into it. And so he says that when general relativity became well accepted, people dropped this whole idea of the temperature effect, because it's not accounted for by the gravity, the general relativity, excuse me. But nonetheless, he picked up doing this research. So it's not just him. There are several others, and hopefully other labs will jump on the bandwagon to help clarify issues in this area of research.
Well, you would think so, because this is the purview of the dissident scientists. And of course, mainstream tends to just anything that's not according to Einstein gets kind of So anything you would
Dmitriev, Dmitriev is fairly mainstream as it gets. I mean, he's presented and has papers and books on gravity at symposiums all over the world. He's been an invited person to present his work. And so I wouldn't call him, an outlier or some kind of fringe character in this area of research. He's been. Why would major conferences on gravitation be inviting him to present his work?
I don't know. I mean, we have Bill, and he's a dissident scientist, and he still gets invited all around everywhere as well. I don't think you get any more dissident than Bill, but it happens. But yet he's a dissident scientist that couldn't be employed by any major physics lab anywhere in the world because he's a dissident, thinks differently, and that's okay. That's why we exist, because we love people who think differently.
Well, I agree with what you say. Dmitriev definitely would be in the dissident category, since he repeatedly says, I mean, he sent a huge volume of basically, I guess, all of his papers, and on gravity anyway. And he says over and over again that his work tends to question the equivalence of inertial and gravitational mass, which calls into question general relativity. He's saying this over and over.
Well, I don't know that anything that we've discussed, and I'm a little bit confused because it doesn't have anything to do with the equivalence principle per se. All you're saying is that the measured weight of an object sitting on the Earth varies according to certain conditions such as weight or rotation. That doesn't really have anything to do with the equivalence principle, which is to say that objects falling on the Earth fall as if they were accelerated equivalently to as if they were being accelerated. I don't know that this has anything to do with that. This is about the measured weight of an object, not even dealing with its, say, mass. We're talking about scale weight here. Except for the rotation when you do free fall, that might have something to do with the acceleration, but still nothing to do with the equivalence principle, which is to say that all objects fall at the same rate. So would you agree with that? I don't know that what you've explained had anything to do with the equivalence principle.
Well, I'll defer on that, because I don't want to get into being a spokesman for Dmitriev. I invited him to participate, him or one of his colleagues or students, and they may be on some other. He may have left a comment or something. I don't know whether he's here today, but
he's still alive. That's the problem.
He should speak for himself on that subject. I think.
I love it.
Rather than me attempting to put words in his mouth.
They're like super old, or they're already dead is the problem. So, but if Dmitriev is still alive, it's like, yeah, we would love to have him on the chat here and represent what he's saying, right? Then we could ask him, what really did happen with the vertical rotor. Because I guess, say, in my theory, I would say vertical rotor, I predict 100% no change. You see any change in the rotor, then I suppose my theory is bunk. So that.
Well, if with these vertical rotor, in the paint mixing analogy, after a long time, you will mix the paint. It'll just take a lot longer than if you had a mixing which would mix contents at the bottom of the can with the top of the can more directly with each stroke. But by the way, pending is I've asked Alex Dmitriev to comment on my bibble babble predictions of many of the results of his studies, and so that's pending. He may come back and say, yes, what I think your theory is bibble babble. Or he may come back and say, wonderful, this is like something which appears may have some substance or whatever, but that's pending. He may or may not respond, but if he does, I will be interested to see what his response is.
Well, I just had one comment. I have just a basic problem with your entire premise that you have this higher bit density on one side and a lower bit density on the other side, and according to that, my head should head towards the higher bit density, right? That's. I'll just have to say I have major problems with that whole concept because there's no reason
Well,
why that should be.
That's all else being equal. And remember,
Yeah, all else
gravitation
being
and
equal.
gravitational force is thought to be very, very weak. Okay. However, it is strong enough that I can see right now Dennis is resting in a chair. He's not floating around the room. And that Franklin is sitting and he's not bobbing up and down in his chair. So that this very weak effect of this very weak effect of quantum density gradient in the law, what the law of motion is saying, it, appears to be quite effective to keep me and everyone else sort of seated and in contact with Earth as opposed to floating around weightless.
The question is that if I have something that's a higher density versus an area of a lower density, and you put something in between it, you know, typically that means it goes towards the lower density area. Like if it was air, you have an area that's high density, you put a ping pong ball between the area of the high density and the low density. Well, you can see that the high density would impact the ping pong ball more and cause it to go to the lower density. Now, I don't know whether this is just a positive, negative thing in your thing, but generally speaking, things should move to the lower density if it's any kind of.
I think you're referring to. I think you are referring to the diffusion laws. Okay. Yes. If a odorant is released in one part of the room, the particles will disperse throughout the room. They will seek out the lower density areas, if you will, and that's statistical mechanics. But I'm not talking about the particles diffusing. I'm talking about a gradient of quanta in the perfect vacuum portion of the energy content of a volume. I'm not talking about the particles.
There's no reason for any thing in your thing to go away or go towards the higher density. That's just kind of the opposite of nature. To
well, the reason is probability. If your criteria for a particle is, let's say, 3 quanta in a location, like I showed in that picture with all the little circles and dots and things. If a quanta moves up to the lower density area, it's less likely to form a particle than if it moves down to the higher density area, all else being equal. So if the probability to go up or down is equal, those that go down are more likely to form particles. So it's a statistical argument, if you will.
And why would it care? Why would it? See, because nature.
Well, in binary mechanics, none of the quanta have any consciousness to care about you, about me, about is there suffering on Earth and starvation.
No, but
they don't have sentient human feelings.
Nature
Why would it care?
And nature tends to say run down or increase entropy. That's why a lot of these things happen. Like, you know, like you say, the sense particle has no consciousness, but entropy would drive it towards the region of lower concentration, right?
I'd like to have somebody present something on entropy to educate me a little bit, because from what I can see, I'm an example of anti-entropy. I and Franklin and Alan, Dennis over there are all compositions which are entirely contrary to the whole concept of entropy. So I'd like to have somebody clarify all that crap to me, because from what I can see, it's a whole bunch of crap.
Well,
I largely agree.
Our existence is an example of everything we build is an example of anti-entropy. Absolutely.
Yeah, I mean,
if we thought everything just runs down, then we should just not exist. We should just be a pile of hydrogen. Is what we should be. But yet, in general, we notice that, you know, buildings fall apart, we die, we return to the earth. Without the input of deliberate energy, you know, entropy takes over. So perhaps that's one answer, which is that to maintain ourselves requires constant active work on our part to keep things together, right? The calculator did not get together all by itself. We had to have machinery and lots of sophisticated actions to put this together. But left to itself, in a million years, this would just become a pile of dust. So that would be nature's entropy at work.
Part of the difference is between the definition of a closed system and an open system. And a lot of these entropy talks, they're talking about a closed system. But in nature, I don't know of any closed system. It's all open systems. And so you get an energy input into the open systems, which maintains and even allows growth of the systems. But it's all open. But when people start talking statistical mechanics and entropy and all that stuff, they're mostly talking about closed systems, which don't occur. They don't exist.
Yep, that could be a possibility there. Although I would just, let's see here. So we have Dimitriev's results there, which I think are at least consistent with, say, my theory. It could be consistent with James's theory. I'm not sure that the rotation can be explained by Bill Lucas's theory. And I'm still not convinced that the rotation, see, the way you could tell the difference between my theory and James's theory is that James' theory would predict that there still should be some weight decrease in the vertical rotor experiment, but I would have to predict 0. So if we did that experiment carefully, we could determine which theory to throw out, either mine or James's, right? If there is some weight decrease, then we would have to accept that James is closer, and I would have to say that mine is wrong, because mine clearly predicts 0 weight loss in the vertical orientation. So,
okay, well, that experiment has been done. I believe, if I'm not mistaken, that in the case that regardless of the orientation of the rotor, there is a weight decrease. And this goes all the way back to the lathe weight demonstrations with regard to ordinary gyros, okay?
No, that doesn't have anything to do with this. He's that's a non sequitur in this case. What lathe weight we're doing? He wasn't saying, he was claiming that, you know, the weight due to gyroscope goes to like 0. I mean, not some small little bit, just that's not relevant. So, but if you can find a reference, maybe we should do that. We should each go and see what they can find the supporting experiment and see what the case is. I'm sure it's out there. That's not going to be obvious experiment to do in these kind of cases. So, okay. So, but that was interesting. So let's see here. So let's get off of James's, what is that? Bibble babble? Okay. So we were talking though, I think we can now continue on with our little discussion about magnetism. And so last week we were talking about some of the properties of magnets, you know, mostly about permanent magnets, right? So what a permanent magnet could be, but those are pretty complicated examples of magnetism. It's like the simplest case of magnetism, I guess, would be a straight wire which has current running through it. That is the simplest system that generates what we would recognize as a magnetic field. And what it does is that the magnetic field that it generates is like an arrow that goes around in circles around the wire. This is how they express that magnetic field. But the magnetic field itself seemingly must always exist in the presence of moving charges. I mean, there's actually a question, and maybe Bob can comment on this, that really that there is no per se separate magnetic field, but that you should look at it purely in terms of the moving charge that creates it, right? Is that something you're kind of expert on that, right, Bob? You can comment on that.
Yeah, I would say that there is no magnetic field. There's just an interaction of charged bodies with a Coulomb field, and different motion of the different bodies generates a different force or realizes a different force. But so no magnetic fields.
Yeah, that's certainly one way of looking at it. I personally think that that's may in one sense be true, but it's kind of an extreme viewpoint, I suppose, because there does seem to be this different thing, right? It's that reacts differently than charges. But I think I agree with the view that what we have here are interacting moving charges. So if I have a wire, it's got charges moving through it. What it interacts with is with the other charge that's approaching it. They're like an electron. So the only thing that's really important is, what is that interaction of the wire, of the charge that approaches the wire, right? So
I wouldn't start with a wire. I'd start with the most fundamental case of two charged bodies, what I would call a source charge body and a test or detector charge body.
well, that's strictly electrostatics then, right?
No, because they're both in motion. By the way, talking of motion, I find in a lot of textbooks, which drives me crazy these days, where they say that the drift velocity of the electrons in a current, or the velocity of a particle, or velocity of anything, they don't define that sufficiently, and the student reading the textbook is left to infer which coordinate system or reference system is being used. Because if you just say a velocity, an object has a velocity, and you say nothing else, you got to realize that what you're saying is that object has all velocities from 0 to speed of light or beyond, if you believe that objects can actually travel beyond the speed of light, all at all velocities at the same time.
Well, I kind of disagree. I mean, why could you just say use the laboratory frame there?
But see, you just clarified. You specified a particular reference frame. Okay. What happens a lot, particularly in electrodynamics, from what I can see, is they just say the particle has a velocity. Yeah, but velocity with respect to what? They don't always and consistently specify that. And that's part of the problem, at least in my opinion, with electrodynamics.
Like I said, I would say it's always presumed to be the lab frame. What other frame could it be? Right?
The detector frame. You put a detector in the lab, but that detector could be in motion in the lab,
which would have velocity relative to this laboratory frame. So it's still
the key thing is to have the relative velocity, that is the velocity of the detector and the velocity of the source particles being measured from the same reference frame. But the source and the detector can be in motion relative to each other. And if you do that, then your electrodynamics becomes independent of the reference frame that you specify, because you're only concerned about the relative motion between the sources and the detector. And that's one thing that I think classical electrodynamics has gotten wrong, is when they go and define, for example, a current or a current density they're mixing up what they're talking about as far as the velocity of the sources. And they're forgetting that it should be with respect to the detector, because typically they specify a current as the average drift velocity of the charge carriers, the electrons in the wire, with respect to the positive ions of the wire. But that's not the velocity with respect to the detector. Anyway, and that's one reason why this concept of magnetism gets all messed up. If you read, for example, the very first sentence of Einstein's 1905 paper on the electrodynamics of moving bodies, and now I'm reading from something I've written, but anyway, Einstein writes, quote, "It is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena." End quote. That's Einstein in German, translation German to English. What he's saying is there's something wrong with Maxwell's electrodynamics when you have charged bodies in motion, which led him to propose his special theory of relativity. And what I'm saying is if they went and redefined what they meant by velocity to be the relative velocity of the source with respect to the detector, then electrodynamics becomes reference frame independent, because your charge density function now becomes reference frame independent, and therefore your vector potential function becomes independent, and the magnetic field becomes reference frame independent. But they don't. And so it's screwed up this reference frame independence of physics.
Well, Bob, you kind of lost me. But I wanted to ask you,
Okay.
based on your knowledge, so you said we should just start with two particles, right?
Right.
So let's just start with two particles. Let's just kind of make things simple here. So, oops, just a second here. Let me put up my picture here and mute Dennis here. Okay. So, in the simplest case, we have a particle. If they're just static and if they're, say, oppositely charged, then we know the reaction is for them to come together, right? So that's Coulomb's force. That's the most basic thing. Now, with our magnetic field, we have, the only difference is that we have some particle in motion. So we have some, and I don't know that it's multiple particles in motion, right? So you got a stream of these particles, say, heading into the screen here, right? So that's what we think is as a current. So now we have this situation where we have all these particles. Maybe we can just think of them going one at a time. And we have this other particle over here. And in magnetic field, this particle is does not feel any force. As long as it's stationary, just sitting in space, it doesn't feel any force, any net force at all. So that's one property of the magnetic field that's kind of mysterious, right?
Well, I would have started differently. When you held up both of them and you said, I'm starting with the static case, I say, that's not correct, because the Earth is spinning around, the Earth is orbiting around the sun is going to, there's nothing static in what you're showing, except for the velocity difference between the two particles. That is a constant, okay, but they're not static. They have, each of those particles have all velocities all at the same time.
I think you're
but relative to each other, the velocity difference is constant. And so that's the distinction that's going on here. Now, if you want to change the velocity difference, one particle with respect to the other, then you are, okay, so you're moving one particle with respect to the other particle, okay? Right. And now the force is going to be different, right?
Apparently.
Yes.
This is the thing that causes
Right.
what we think is the magnetic effect.
Right. Now you could hold that one that you're moving still and move, right, hold that one still. Now move the other one, the orange. Yeah. There you go. How can you tell the difference? You can't really tell the difference if they're
Sure, I can.
if
I'm
it's,
sitting in the
if it's
laboratory
constant
frame.
velocity. Right.
I'm
But
sitting in the
I'll go.
laboratory frame.
Right.
I know which one is moving. This one definitely moving. This one definitely not. Laboratory frame, for sure.
Right. But the guy on the bicycle that is moving with the one that the white one that you're moving will see that orange one move, and the white one he'll say is stationary.
Yeah, but laboratory frame. This is the one that's actually moving.
Right.
So I mean, I am of the opinion that the laboratory frame takes precedence. But the guy in the bicycle, his frame don't matter.
Unless his laboratory is on the bicycle. It's his laboratory frame. Why is your laboratory frame so special? But
Because
anyway, for
I'm
magnetism,
sitting in the I don't know, the ether, and the ether is entrained on the Earth, and that is the preferred reference frame. I guess that would be my response.
but that's why I say do the velocity difference, and then you don't have to specify any reference frame. It's independent of the reference frame. Because when it's the velocity difference is all I can say. The analogy which I have,
a velocity difference, and I kind of see your point. Oh, I kind of disagree.
okay,
I'm thinking that when you start thinking that all reference frames are equivalent, then you start getting into those twin paradox things and stuff like that don't make any sense.
but physics should be specified. Physics laws in the mathematics should be reference frame independent. Because it shouldn't matter if I do an experiment on the Earth or on the Earth in a train that's moving at a constant velocity, or on the Earth on a boat that's moving at a different velocity. The experimental results should be the same in any reference frame, as long as it's not accelerating. And therefore, physics should be expressed as reference frame independent. Anyway, for magnetism, I like to think of it as a golf ball being hit in still air. So you're out on the golf course, there's no wind, and you hit a golf ball and it's straight. Then you go and hit another golf ball and you slice the golf ball and it will curve through that air. Why is it curving? It's not a special air. It's not, it's not a dark matter kind of air. No, it's that the particle is moving relative to the air molecules differently. In one case, there is no spinning of the golf ball, but it's still moving through the air. And the other case, it is spinning and it's moving through the same air. So it's a coupling of the detector, the golf ball moving through the air, with the field, the electric field, or the air that the object is moving through. And that's what's different is the way that the objects are moving with respect to each other. That's all that magnetism is.
You're saying it's like the spin of a golf ball. Although that kind of interaction is pretty weak. Right?
Yeah, but it still slices. I can barely hit a golf ball straight without slicing it. And you can really get the golf ball to deviate a lot. Or a tennis ball, or, a ping pong ball, or anything that you
Well, the
want.
thing is, though, is that the magnetic field doesn't seem to be a property of the incoming particle. I don't think
It seems to be a property of the relative velocity, because as you said, when you hold the two up together and they're not moving with respect to each other, you don't see a magnetic force. It's only when one is moving relative to the other one that, oh, gee, now there's a deviation that was not there before. And that's the kind of thing we call magnetism. But it's just a relative motion of one charged body to another charged body.
Well, it's more confusing because, this is like due to multiple particles. Like if you have a CRT beam, I guess that would even be a simpler situation, since they can
Sure.
now disregard all the atoms of the wire.
Sure.
Right? It's a CRT beam.
Right.
And if we have a charged particle over here, you shoot a CRT beam past it.
Right.
This thing doesn't move.
I would say it does move.
That's the mystery.
I would say it does move.
Why would you say it moves?
Because the relative velocity between the two, the source beam and the test particle or detector, that relative velocity is now different. So it's not
It
the
is.
static.
This is the
It's not
mystery.
the static phaser.
Experimentally, this particle does not move. I mean, you've got all this other motion going on with the CRT beam going, all the electrons flying past it. And this particle doesn't care. That's basically what the Lorentz force law says, is that if this particle is not in motion, and I guess once again, we have to clarify, laboratory frame, special frame, we got to get to pick one frame, laboratory frame, that if you've got motion going this way, that Lorentz force law says that this particle feels no force. It stays right there. But if this particle is say, coming in, you've got your particles coming in this way, and you have this particle coming in at a tangent, what happens is that this particle is deflected. It actually deflected in the direction that the current flow is going. If you figure out this whole, B cross C thing with the curl and blah, 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 and the circular thing, you find that the particle coming in will be like, for example, go with the flow of the current, or it'll go against the flow of the current. But generally speaking, the vector force is going to be in the direction of the flow. See, so that's the mystery. You got these particles coming this way. You got this particle coming this way, and somehow, like it's being swept up to a river, it will go along. It will be forced along the same direction as the moving particles. See, now, I'm curious.
By the way,
do you think that happens?
By the way, the Lorentz force law, I think, is only applicable to currents in wires.
Certainly, yes, because it says there's an electrical. Well, actually, it applies to electrons in motion. That's what's in the Lorentz force law. You've got an electron, you've got velocity, you've got charge.
Right. But
you've got this cross thing.
It's different because in a wire, you have positive and negative charges, not just negative charges. And so if you move the wire with the electrons, then you still get an effect on that test or on the detector.
Yeah, you would think that's an interesting thing. You would think that if I have a loop of wire and I just start spinning it, that in itself should create a magnetic field, right?
Well, no, because you don't have the relative. Let me back it. Yes.
No, I think that is true. I think
yes.
That you spin
the charge in motion is what you would call the magnetic field. Yes, but there's two: a positive from the positive charges, and from the negative charges, and they sum up. Those quote unquote magnetic fields, as you would call them, are generated, but their sum is zero.
Oh, they cancel.
Yeah.
Okay. Yeah.
So that's why you need a velocity difference between the electrons and the protons and the detector. It's a more complicated system because you got three things going on, not just two.
Okay, so I'm just kind of curious, do you have an explanation? And it's okay to say that you don't have an explanation, okay? If you don't have an explanation, I would much rather you just say, I have no idea how that works, rather than try and come up with an explanation that's just kind of regurgitating the mainstream viewpoint. But do you have an explanation for why this specific case, we have the electrons moving in this direction, And as long as this thing not moving, it feels no force. But as soon as it comes in, it kind of takes the same motion as the electrons moving that way. Do you have an explanation?
I would explain that by saying first throw out the Lorentz force law.
Okay.
And
good.
and
Okay.
and I would love to do the experimentation, but the force law which I use mostly is Weber's force law, and Weber's force law says if you have any relative velocity between the source and the test body, then there is an additional force component. So in your case, what you're saying is when you had that stream of electrons and you have a test body coming in perpendicular to it, there is a relative velocity difference and it's going to feel a force. And it's going to entrain, I guess you might say, the test body.
Well, it might, but the mystery is that depending whether this is positive or negative, it'll either go with the flow or, in the opposite case, it will go against the flow. So
Sure.
it's like that's.
Sure.
So
Yeah,
how can it
because
go
there's
against
an
the flow
additional
if it's an
plus.
agreement?
There's a plus or minus sign in front of the force law,
Yeah,
depending
why is
on
that? That's the other things hard to. It's like if it all just went along with the flow in the same direction of the flow, then you could say, oh yeah, it's just it's just like a river and you're throwing a leaf in it, right?
Yeah, but there's a plus charge and a minus charge. And if you're asking why there's a plus charge and a minus charge, I would say take a look at Paul Liavette's work, which is an open system theory approach to charged bodies. I don't know if you know what the brusillator is. It's a chemical reaction which gives rise to stable patterns. I don't know if you have ever seen any of that kind of work, but Paul Liavette has a lot of writings on what he calls his model G. G is in George, and he has a very nice model for electric bodies, positive charges, electric charges, as open systems.
Yeah, but how does he explain it? I mean, I'm always curious because I really there's just like a dearth of explanations. But if it's a proton, this is electron. Why do they come together?
Because, as James was saying, there's a gradient difference in the space between them.
And how does that gradient cause these two things to get pushed together?
Well, gradients are like the slope of a hill. You either roll down a gradient or roll up a gradient.
I mean, if you had a gradient, a hill, and you're in the middle of space, that gradient does cause nothing. So,
no, you got to have a gradient at the local location of where you are. Whether it's a gravity gradient or an electric field gradient, or if it's a...
See, that's circular. That's circular. You're using gravity to explain an attraction force. That's not really allowed.
Yeah, just not so much explain, but just given an example of a gradient. The gravity
And
field would be a
don't
gradient.
exert net forces. They don't. Let's see here. How do I explain net gradients? Don't. Let's say we have the I don't know. It's kind of hard to come up with a gradient that isn't already in another gradient. It's like in the ocean, the density of the water is higher than the density of the what's out. But does that density, that density?
And that's why
a gradient? I guess you could say it does, but it's still.
That's why a bubble in that water will travel up, because there's a gradient difference.
Let's say I make a gradient by just writing the numbers 0 through 10 on a number line. Okay, there's a gradient. The letters 3 and 4, and there's no force. There's a gradient there, but cells don't generate forces.
You're breaking up, I'm sorry, too much. I didn't follow it a lot, but there was something about a gradient, 0 to 10, and something about a sound.
Okay.
Sorry, I
There's
couldn't follow
0
it.
through 10 on a piece of paper, right? That's a gradient. And I could put my Lego brick anywhere on that number line, and it will not experience a force.
The Lego block needs to interact or couple with that 0 to 10, whatever it is. If you do not couple that block with that 0 to 10, then that block is not in a gradient.
Okay, let's suppose that it's coupled somehow. So why should the gradient cause it to go from one place to another?
Because it's trying to minimize the differential across its body. It will be
Why would it do that?
4.1 on one side and 4.0 on the other side, so it will try to make it the body will move to try to go to an equilibrium position or to a lowest energy position.
And why would it do that? I could be like a child. If you ever done this, it's like you'll talk to them.
Right. It's very annoying.
And every single answer you give them is like, why? Why?
Exactly.
Why?
Yeah.
Why?
Yeah.
I'm just going to do that. I'm going to keep doing that to you.
It's very annoying.
I would assert that
understand.
that argument can never be won. That argument can never be won because, you ultimately you can't justify why it should go towards a gradient. There's no explanation. It's something you have to postulate.
Well, you say that it's an
as a
open
counter
dynamic
to that-
system. Open dynamic system that couples with the environment that it's in, and the couple means that there's a force when there is a gradient to that environment. That's about all. Hi, Eric.
Okay, let me just give you. We're almost at the end of our conference here, but I want to give you a different way you could think about it that does not involve this whole infinite Y series, which you ultimately can't answer. Which is that the only times we see particles change course is if they actually collide into each other. There has to be some physical collision happening in order for any particle to, otherwise it will just follow the same old dirt. In the case of positive and negative, the particles that cause them to be literally pushed together. So
You're breaking up.
So it's not a gradient.
Yeah, you're breaking up a little bit.
Literally,
too much
there
again.
is the only reason why we see the positive charge come towards the negative charge is because there's something else. There's something else. Oh, okay. Well, are you guys hearing me okay? Likey here, so sorry. But the meant to say that these things come together, you say that there is some outside proton, other particle hitting this particle, which is causing them to come together. And actually, I don't think nature can generate attractive.
Let's take if you'll pardon me for saying so, let's take a Bill Lucas point of view, and that the particles that you're talking about are made up of the fields. And so a particle would not have a discrete boundary as you're holding up. No, so a particle
What does that mean?
really
That means
extends.
nothing. That's impossible.
No, it's not. Take a look at a tornado.
Take a look at this Lego brick. There it is.
Right.
That's what
Right.
makes sense. It's not a conglomeration of a field, whatever the heck that means. It's a
Sure
solid
it
piece
is.
of something.
Which is made up of electrons and protons. An electron is a field in like a tornado. It's like the air of a tornado, which extends really far away from the tornado, but the core of the tornado kind of looks like a solid.
And the field effect of a tornado is like extremely limited, like like 1/r to the 4.
Well, sure, it's a
Or
tornado,
something.
and it's a tornado, and it's bounded by
drops
space and
way
by the
faster
earth.
than an electrostatic field.
Yeah, but the tornado
This
is
is why I disagree with this entire idea that electron could somehow be a vortex. I mean, that's just my opinion, but it just doesn't seem to fit.
it doesn't have to be a vortex.
That's just my opinion. But
Yeah, but look at Paul Leovet's work. It's not so much a vortex as it is a reaction diffusion kind of interaction or process.
let's see here. Yes. we
Anyway,
have some
before-
problems. Well, it
before
looks
we
like
go,
we've kind
James-
of gotten to the end of our discussion here.
Before we go, James, I just want to say thanks very much for bringing Dmitriev's work. I'm going to go and look that stuff up. That's very interesting. Thanks for bringing it to us.
Yes, thank you, James. So just kind of summarize. So we did get a little bit of criticism that James has kind of been monopolizing the science chat past couple of weeks, and that's probably true. But I kind of enjoy when people bring stuff. It's better than hearing me kind of randomly do my bibble babble or whatever it is. But James brought us that very interesting points of information on the effects that the gravity, the weight is not constant, that it seemingly varies by temperature, or you can see it varied in optical lines, or you can see it varied in a gyroscope just statically sitting on a scale, or you can see the effects of a gyroscope being dropped, and there's a big difference between being horizontal and vertical. So, and we kind of discussed, why that should be. I was drilling James pretty hard about, what would his theory actually predict that, right? Or whether that was kind of a post-diction, or you just kind of fitted it in. But I think we kind of got it a little bit more clarified that it's of what would be normally the gradient, I guess. So, and but there's this difference between the vertical and the horizontals. And yeah, take a look. I think there is actually no weight difference in the vertical orientation that's measurable at all, which would be kind of a separating factor between the competing theories. And we explained, like, I have my theory, James has his theory, Dr. Lucas has his theory, 3 possible theories explaining the same 4 effects. So I personally don't doubt that those effects exist. I think they probably do. And it's the contest to see whose data fits all of that at the same time in the most cognizant fashion possible. So yes, so we discussed that, and then let's see here. Then we got a little bit back into the magnetic field, just trying to break it down into its most fundamental thing. Bob has a big bugaboo about relative frames. I personally don't. I think just use a laboratory frame. It's good enough. Good enough for Franklin work is what I normally say. And trying to figure out what actually is going on in the magnetic field case where we have a particle coming in, not moving, doesn't do anything. But if it is moving, then we see some of this, what we call magnetic effects. And discussing, well, maybe, maybe we shouldn't be calling a separate magnetic field, but it's so freaking complicated that I think we probably should. But unless James has another thing next week, we'll probably continue on with another step in the magnet to just Google, how the magnetic field effect works. And other than my videos and papers, you'll find actually nobody even attempting, not even dissidents, attempting to explain what the how the magnetic field works, right? So just literally Google how the magnetic field works and see if you can find anyone who's even willing to put up any kind of explanation. They recognize, what a magnetic field does, but actually physically explain what is going on there, right? And I'd be interested if you could find some articles. I think there's like only one other guy in the entire universe who thinks he's got an explanation for that. It looks like David has got an explanation in his book about how magnetic fields work. Oh, excellent. And so I'd like to hear all about those. And someone thinks I should grow a beard as well. Okay. No, I'm not going to do that. Okay, but that will do it for so that for your early risers in the West Coast, 7 a.m. and 7, 8, 9, 10 o'clock in Eastern time, or if you're in some all right. So thanks, and see you next week. Upgrade my internet.